Hello, how's it going? Welcome to the last non-Python topic in our course. So, congratulations on that. Hopefully you had a chance to look at the reading and then watch some of those videos. Again, for the longer ones, you didn't have to watch all of them, but they are good. They're all good. So kind of pick the one that you find most interesting and try to carve out some time to watch it because they are interesting. And artificial intelligence is something that obviously is going to have huge implications for us going forward. So the more kind of comfortable you are with it, the more aware you are of it, the more cognizant of its applications, all the better. All right, so we are going to go through some of the notes here. And then we'll go from there, and you're going to end up doing a lab that works with some of these concepts. All right. So first things first, just kind of the big historical name when you're talking about AI is Alan Turing. There was the video there that I had you watch on him, but leader of the group that produced Colossus to crack the Nazi codes, wrote a landmark paper in 1950 that asked the question, can machines think? Proposed the Turing test. We'll talk about what that is in more detail in a second. But it was a way to determine whether a computer has achieved intelligence. And there's something called the Loebner or the Loebner Prize or something. It's got actually mixed reviews in sort of the artificial intelligence community. Some people think it's more of kind of like a publicity stunt that doesn't really push AI forward, but it's still, it's kind of uses his test. It keeps his name kind of in the conversation. Again, more recently, if you saw the movie The Imitation Game, that involved him. So just kind of a big, important figure in the world of artificial intelligence. All right, so the Turing test, more specifically, is this idea where you have an interrogator. All right here. That interrogator is communicating with two people. One of those people is an actual human being. One of those people is an artificial intelligence. And if the interrogator is unable to tell which one is the human and which one is the artificial intelligence, then by Turing's definition, you had achieved intelligence there. If you could fool this interrogator into thinking that an artificial intelligence was a human, then that's sort of passing the Turing test. Because obviously there's a lot that goes on in being able to carry on a conversation. There's context, there's metaphors, there's similes, there's all sorts of language, and it's a very difficult task to do. So if you could actually have a computer sort of fool somebody and say, yeah, I've got no idea which one's the person or which one's the computer, or worse yet, even think that the human is the computer, then you've achieved a pretty hard standard, and you've gotten over a pretty big bar there. All right, so that's kind of the idea of the Turing test. All right, so more generally, AI is the field of computer science devoted to making computers perceive, reason, and act in ways that have been reserved for human beings. So, what has this already provided? We've got systems that can produce expertise in medicine, science, and other fields. We've got robots that can outperform humans in many tasks. Automation is a big thing. World-class electronic chess players, if that's your thing. Also, recently, Go is another abstract game that AI has sort of kind of conquered. And then, things that we're looking at in the future, obviously self-driving cars is the one that gets all the attention. And that becomes a really difficult task because you have to be able to recognize road signs, pedestrians, other cars, and then make decisions in accordance to all of those other factors. Artificial tutors. There's actually a funny story of an AI class at Georgia Tech. And the class was online, and they used like an artificial intelligence to answer students' questions on like a message board that they had set up. But the students didn't know that they were interacting with an artificial intelligence, and it wasn't until the end of the course that they let kids know that when they were asking these questions, a lot of times the answers were just coming from an artificial intelligence, and most of them had sort of no clue there. So that sort of stuff. And then healthcare, just being able to better analyze things, whether it's test results, whether it's medical images, whatever it is, just different applications in improving sort of healthcare outcomes. I mean, who knows? I'm sure certain AI technology is being used right now to kind of analyze the coronavirus and what's going on and developing treatments and vaccines and all of that stuff. I'd be shocked if AI didn't have a role somewhere in that. So again, lots of applications for the future. All right, so 2 common approaches to AI. One is using computers to simulate the human mental process. So basically, analyzing how we think about something, analyze how we solve a problem, and then trying to mimic that inside of a computer. Problem is, it's actually kind of hard to sometimes put what we do into like a formalized process. So much of it kind of happens intuitively and just automatically that it's hard to sometimes sort of encode that in a series of rules that a computer could follow. And that's kind of what that second one is saying there too. I mean, human intelligence includes unconscious thoughts, insights, and other mental processes. So all stuff that's hard to sort of encode into a computer. There's just difference in the structure of a human brain versus a computer. The brain isn't exactly a series of transistors and logic gates and everything else. So there are just differences that make that approach difficult. And often, people have advantages over machines and machines have advantages over people. So it may not always be the best choice to try to force one to act the way the other does. Like, it's not great to make a human try to act like a computer. And similarly, there's problems when you try to have a computer do things the same way humans do. So then the other approach is to try to design intelligent machines independent of the way people think. So recognizing that a computer can do things better than a human can. For example, adding a 4,000-digit number, a computer could do it in a fraction of a second and never make a mistake. Can't really say that for a human being. So taking advantage of the speed of computers, the accuracy of the computers, and trying to simulate, human thought, but maybe not exactly go about it in the same fashion. All right, so let's take a look at kind of a common frontier for AI. So one of the early applications of AI was looking at game playing. And the reason that game playing works well with artificial intelligence is there's usually defined rules, there's usually a limited sample space, there's clear goals, so it makes it easier to kind of set upon this and say, all right, I know exactly what the limitations are, I know exactly what's going into this, and kind of coming up with a game plan to sort of figure out what's going on. So some of the first popular ones were checkers and chess. And again, they're just well suited for all the reasons I kind of just mentioned. So this kind of developed techniques that get used in other applications, but they sort of got their start here in game playing. So searching is looking ahead at all the possibilities generated by each potential move. So basically saying, all right, I'm going to look 30 moves ahead and look at every possibility and then see which paths are the highest, have the highest success rates. Heuristics is generating rules of thumb, like if you see this, do that. If you see this, do that. But if you see this and that, do this other thing. Pattern recognitions, so looking for certain structures and certain setups that might guide your decision making. Like if you see this certain arrangement, then we're going to go from this playbook. But if you see this arrangement, we're going to go from that playbook. And trying to identify patterns and then use those patterns to help make decisions. Again, these techniques were developed with game playing, but they've since been expanded to all sorts of other fields. And then machine learning, learn from experience. So usually that involves testing over and over and over and over again. So trying things, recording the outcome, and then slowly just saying like, all right, when I did this last time, it got a good outcome, so I'm going to do it again. When I did this last time, it got a bad outcome, so I'm going to try something else. And if you do it, thousands and thousands of times, or even millions and millions of times, because again, that's where a computer has its edge. It can do something millions and millions of times, and it won't take that long to do it. You can slowly sort of learn from experience how to play in certain situations, or how to drive a car in certain situations, or whatever. But this idea of kind of just simulating things over and over and over again, and kind of making decisions from that point. All right, so what we're going to do is we're going to just go through a simple little game here so you can see how searching might work. All right, so here's our simple little game. It's the game of NIM, but a simplified version. Player 1's symbol is X, player 2's symbol is O, and the board consists of 13 blank rows. So player 1 takes a turn either filling in 1 or 2 blanks with their symbol from left to right, and then whoever fills in the last blank wins. All right, so this is where if we were in class, I would challenge each of you to a game. Clearly you would lose because I'm the superior player, but we can just sort of, simulate what that might look like. So I might be like, all right, we'll start with an X, and then you think you're all clever, so you're like, oh, all right, I'm going to go double O. I'm going like, no big deal. I'll just go double X, and then you're like, oh, really? So I'll just go single O. I'm going to be like, single O? I'm going to drop a double X on you. And then you're like, oh, yeah? Well, I'm going to drop a single O, and then I'm like, yeah, big deal. I'm going to drop a single X, and then you're like, oh, man, this didn't work out for me. And I'm like, you're right, it didn't work out for you, because then you play an O, and then I drop the double X, and it's game over. And then you're like, that's like beginner's luck. Like, I would totally beat you next time. And I'm like, no, you wouldn't. Not a chance. So you're like, yeah? And then I'm like, sure. And then you're like, all right, let me go first. I'm like, fine, go first. So then you drop a double O, and I'm like, boom. And then you're like, I see how you're going. And then you drop another double O, and I'm like, no big deal. And then you're like, I don't know what to do here. And then you're worried, so you're like, I'm going to play conservative and drop an O. But then I'm like, all right, you're going to play conservative, I'll play conservative. I drop an X there, and then you're like, and you're stuck, and you play these double circles, and I play an X, and it's game over. So, again, this is what we would have done in class. After beating you, I would have, gloated and celebrated my triumph. I maybe would have eaten a piece of candy, just something to really cement my victory. All right, so just imagine that happening. Imagine the disappointment at being unable to beat me. All right, so once you have that in your head, then we'll kind of look at how a computer might approach something like this. All right, so a computer might generate something called a search tree. All right, and a search tree represents all moves in a game for both opponents. The paths down a search tree represent a series of decisions made by the players. All right, so let's start with our game. And we're going to make it simple, because otherwise we won't have enough room on the sheet. And we're going to start with just 4 blanks. So we've got 4 blanks. All right. So player 1 is going to take their turn. All right, and we'll make player 1 the X here. And player 1 has 2 options. All right. So player 1 can either put down a single X, which then leaves 3 blanks. Or they can put down a double X, which then leaves 2 blanks. All right, so these options are coming from player 1. And then after player 1 makes their move, player 2 gets to make a move. All right, so player 2 can either go and put down 1 circle, leaving 2 empty spots. Not a great move, but we'll see. Or they could put down 2 circles, leaving 1 empty spot. Also not a great move. But what can I say? I'm good at this game. And then if we go down this branch, all right, we've got a couple of options. All right, if player 2 is smart, actually we'll say player 1 is not smart. All right, if player 1 is not smart, they're going to put down a single O and leave 1 empty spot. If player 2 is smart, they're going to put down 2 circles, and the game is going to be over. Again, for our simplified, like, mini version here. All right, but this is player 2. And then player 1 would go. And again, player 1's options would be, we could go X and just put down a single X here. All right, not a great move, but I could do it. Or I could go here and put down 2 X's, probably a better move. All right, on this one, there's only 1 branch because I only have 1 option, and that would be to put down the winning X. And then if I go over here, all right, I only have 1 option as well. So put down the winning X. And then again, if I made, most of these, the game is already over, but if I made this 1 bad move, player 2 would get a second chance. And then we would end up in this situation. All right. So from this, all right, we can kind of, this is the sort of thing the computer would generate. All right. It would generate this tree. It would analyze the different paths. And from those paths, it would try to pick the optimal move. So, for example, all right, if the computer was player 1, all right, the computer would recognize that, all right, if I start with a single X, all right, I can win this way. All right, this is a win, and this is a win. And most of those are going to be good paths for me to go. Like, as long as I don't make this 1 bad move, if I start with a single X, I'm going to win the game. So the computer analyzes all possibilities and then picks the best possibility based on the entire kind of sample space. You know, versus this situation, like, the only way the computer wins here is if player 2 makes a really bad decision. So this would be a bad starting move. But if the computer's the second player, all right, if the computer's the second player, then, you know, based on kind of what player 1 does, it has to make its decision. So, like, it obviously knows that playing 0-0 would be bad because that only leads to a loss for it. So if player 1 starts with a single X, the computer's going to know to play just a single 0 and then hope that it ends up down here. If player 1 plays 2 X's, I mean, this one's a little more obvious, but the computer's going to be smart enough to play kind of the 0-0 there. So it sort of pulls out all of the possibilities, and then based on those, is able to kind of figure out the best choice. And then with today's powerful computers, they can perform these massive searches really, really quickly. That said, complex games like chess and Go require way too many searches. Like, this is a very simple game, but just think about a game of chess. Like, think about how many opening moves there are. You can move any of the pawns. You could also move the pawns 2 spaces. You could also have your rook come out on your first move. And then once you make that first move, your opponent has all of those possibilities themselves. So the number of options quickly becomes unmanageable, even for the largest, most powerful computers. So rules are needed, and they might not go all the way to the end of the game, but they might go like 10 moves forward and say, all right, if I make a tree 10 moves forward, which branch seems to be the most promising? But that's one of the ways that we can kind of simulate computers thinking. And again, this isn't the way humans play. All right, humans don't list out every single option and then say, oh, let me choose the path that is the highest probability. So we're not trying to have the computer act like a human. We're taking advantage of what the computer can do well. All right, the computer can generate giant search trees. The computer can navigate those search trees really quickly. The computer can calculate probabilities. It can do those sorts of calculations. So we're taking advantage of what the computer can do to make it look like, it's acting human in playing a chess game or playing Go or playing checkers or anything like that. So it gives us this idea or this illusion that it's thinking through the game the same way we think through the game, but it's actually following a very, very different process. All right, so search trees are one way that we can kind of simulate intelligence. Another way that is pretty popular is the expert system. All right, so expert systems, knowledge of a specialized field is programmed as a set of rules. So you can think of this as kind of like the if-then statements that we write all of the time in our programs. The systems ask the user a series of questions, then draw a conclusion based on the rules. So again, this was the example that was in your text, but imagine these are like your potential responses. Apply a turf building treatment, apply a weed killing treatment, apply a basic fertilizer treatment. The system would ask about different variables regarding the state of your lawn. Again, this was like a lawn care system. So do you have bare spots? Is the lawn sparse? Are you dealing with weeds? And then based on responses to those, it's basically just navigating if-then else statements to sort of lead you down the correct path. And a lot of times you'll see these in like debugging things. Like if you ask like Windows to debug something, it'll ask you a series of questions like, did you try this? Is this on? Is this off? Are you seeing a blinking light? Or basically anytime you call like tech support, they have like a series of questions that they ask you to respond to. That's the idea of this expert system. It's basically like encoding tech support into a computer where based on your answer to one question, it knows which question to ask, and it's just you're filtering your way through the system until you eventually get to a response, or you get to, I'm sorry, I don't know how to help you, and then you're like, thanks for wasting my time, and thanks for nothing, you didn't give me an answer, and now I'm upset, and yada, yada, yada. So again, another way that we can do it where we're just trying to take human knowledge, we're like interviewing experts, we're trying to get everything they know, and then encode that into a series of questions that the system can kind of work its way through. So again, simulating intelligence and trying to incorporate it into a computer program. So we just talked about search trees and expert systems, which are kind of two ways to generate artificial intelligence in machines. Again, search trees, you try to list out as many possibilities as possible and then use the computer to analyze which path is going to be the most likely to succeed. Expert systems is more of like a series of if-then type questions to sort of arrive at an answer. You can almost think of it as like kind of like 20 questions to like based on your response to one question, we decide to ask this question, and then based on your response to that, we ask this question, and slowly we kind of narrow it down to what you're trying to achieve. And then probably the one that gets the most attention these days is the artificial neural network. So I feel like that's the buzzword that gets thrown around the most, when you're dealing with artificial intelligence. And it's inspired by the structure of the human brain. It's not to say like it's building a human brain, but it takes inspiration from it. And it uses a network of artificial neurons. And I think the most interesting thing is that it's trained through trial and error, not programmed. So the funny thing is about neural networks is once you kind of set them in motion and you start running them and giving them sample cases, they start to change and adapt. And you as the programmer don't really understand why it works necessarily. Like you understand why the idea of a neural network works, but the individual solution that it arrives at, you don't really know why that's the best solution. And we'll talk about that a little more, but it's kind of an interesting approach to the whole idea. So first things first, how neurons work biologically. And what I'm going to ask is that you don't show this video to any of your bio teachers, because I'm sure I'm going to screw things up and not be as scientifically accurate as I should be. Again, my training's not in biology, so I apologize. But I'll try to do a high-level version of it. So neurons are connected in a network. Each neuron gets multiple inputs and weights, each depending on the synapse's importance. All right, so there's lots of kind of inputs into a neuron. And then as those signals kind of feed into the neuron, if it reaches sort of a certain threshold value, that will allow kind of the signal to travel through the neuron, and then it'll be active. So the neuron's usually either in an excited state or it's not excited. And it gets all these inputs, and when the inputs sort of exceed a specific value, that's what sort of triggers the neuron to fire and allows the signal to kind of propagate through the brain. So a combination of inputs and weights determines whether a neuron transmits an electrical signal, which is chemically based, to the surrounding neurons. So again, each neuron is connected to, I'm not even going to guess the number, but lots of other neurons. It's getting in all of these inputs. Those are the dendrites there. That's kind of where the inputs are coming in, and then based on if it gets basically enough activation and it exceeds sort of its limit, then it's going to pass on the signal, and that signal is going to go on through the synapse, which is then going to feed into the dendrites of another neuron. So kind of one neuron's output is another neuron's input. All right, so again, let's kind of see how this can translate over to a computer. All right. So here is an artificial neural network. All right, so you can think of this right here as your neuron. All right, and it's getting inputs from different parts of the program or the neural network. And to compute the output of an artificial neuron, we multiply each input by the corresponding weight and sum up. If the sum is greater than the threshold, then this outputs a 1. Otherwise, it outputs a 0. Because again, we're still in the world of computers, so our choices are either 1 or 0. So the question says, what is the output of this neuron if the inputs are 0, 1, and 1? So imagine that this one is getting an input of 0. This one is getting an input of 1. And this one is getting an input of 1. So again, this is kind of analogous to the dendrites. You've got lots of inputs feeding into this one neuron right here. And then if we exceed the threshold value, the neuron's going to become excited and pass on the 1, all right, out its synapse, or it's not going to get activated and a 0 is going to come out. So again, you can kind of see the relationship to neurons here. So in this case, basically all you'd be doing is you'd saying, all right, the input is 0, the weight is 3, so that's 0 times 3, plus the input is 1, the weight is negative 2, so 1 times negative 2, and then here the input is 1, the weight is 5, So 1 times 5. And then we would just work that out and say, oh, okay, 0 plus -2 plus 5 equals 3. All right, 3 is greater than our threshold value of 2. So then this would output a 1. All right, this is our output right here. All right. And a slide ago when I said, it's trained through trial and error, not programmed, what I'm referring to is these weights here that feed into each individual, that feed into the artificial neurons, if you will. Those weights might be randomly generated at the start. And then what happens is you start to feed in test cases to your neural net. All right. And depending on whether it passes the test or fails the test or does well on the test or does poorly on the test, these values can be changed. All right. And when you change them and you get better results, they stay the same. When you change them and you get worse results, you change them. And by just running thousands and millions of tests, these numbers get slightly tweaked to get better and better results. And again, the end product, we don't know exactly why the numbers are what they are. The computer just sort of slightly tweaked them until it got progressively better and better grades on the test. All right. So let's just look at a longer example so we can just make sure that we're clear on this. So here we have, several things that are connected. And it says, what is the output of this network of neurons if the inputs are 1, 0, 1, and 1? All right, so what that means is we're going to say this one has an input of 1. This one has an input of 0. And then both of these have inputs of 1. All right. So on this one, all right, it would be 1 times 2 and 0 times 1. So 1 times 2, 1 times 2 plus 0 times 1. All right, that's going to equal 2. All right, which does not exceed our threshold value. So this is going to output a 0. All right, and then this down here, we've got 1 times 2 plus 1 times 3, which is going to give us a 5. 5 exceeds our threshold value of 3, so this one's going to input a 1. All right, and then 0 with a weight of 5. So they just keep kind of propagating through the network, plus 1 times a weight of 2 equals 2. All right. The threshold is a 0. This is less than your threshold, so the output is a 0. All right. And again, this could be for all sorts of different applications. So maybe you've got like a neural network that's trying to identify, stop signs and looking at pictures and trying to identify stop signs. And each of these neurons represents a different thing that it's sort of checking for and different things that are of importance or not of importance. And it analyzes the picture and it sees things that are red and it sees things that are certain shapes. And it slowly figures out, how to tell apart a stop sign from just, somebody wearing a red shirt or so on and so forth. And these numbers slowly get modified, so the weights slowly change, so that the things that it's valuing in the picture are changing. So it learns that, yes, red is important, but it's not just that it's red, it also has to have white in it. And it's not just that it has to be red and white, but the white has to have a certain pattern inside of the red, and so on and so forth. But the computer just does this through trial and error and changing these different weights over thousands and thousands and millions of tests so that it slowly gets the right output. If it looks at a picture and it's supposed to have a stop sign and it says 0, no stop sign, then these weights are going to get modified And we're going to look at the picture again. And does it say that it's a stop sign this time? Okay, good. All right, let's move on to the next picture. All right, nope, it's saying it's not a stop sign when there is one there. All right, what do we need to modify? And then we look at the next picture, and that one doesn't have a stop sign, and it says that it does have a stop sign. Okay, so things get modified, and it's not like a human being going in and like tinkering and saying, all right, well, let's change this 2 to a 4, and let's change this 1 to a 3. The computer is just kind of doing it all on its own, but it's not really intelligently thinking through it. It's just trialing and erroring, but it's doing it at such a phenomenal speed that it's able to eventually kind of end up in the right spot. And that's kind of the big idea behind how kind of artificial neural networks function. Now, obviously, there's a lot more detail. There's a lot more that goes into these. In this course, it's not an artificial intelligence course. If you take an artificial intelligence course, you'll get into this stuff a lot deeper. But that's sort of the general idea. All right. So just a few other kind of notes here. This is a cooperative process. If the input signal is 0, the weight is irrelevant. If the input signal is 1, the magnitude of the weight, whether positive or negative, can greatly affect the output. And then this is kind of what I was just talking about. Where do these weights and thresholds come from? Training. All right. And training is, giving it basically tests, feeding in pictures, feeding in whatever you're trying to analyze, and seeing what happens. So the weights and the thresholds can be initially random, and then training data is used to adjust weights until the correct output is produced. And there's just lots and lots of trial and error that gets done over and over and over and over again to kind of reach a place where it's making the right decision, most of the time. All right. So another big frontier in artificial intelligence is natural language comprehension. All right, and this goes back to the kind of the Turing test that I was mentioning at the very start of having a human being talk to a machine and not realize it's the machine. For that to be possible, there has to be language comprehension. So this has been a huge focus of artificial intelligence pretty much since artificial intelligence was a thing. So an early project was to create a program that could translate scientific papers from Russian to English and vice versa. Kind of think Cold War era. U.S. wants to know what's going on in Russia. Russia wants to know what's going on in the U.S. and so on and so forth. Seemed like a pretty straightforward project. Create a parsing program that could analyze sentence structure, identify each word as a subject, verb, or other part of speech, and then create a program that would just look up the word in the dictionary and go from there. They thought it was simple. After about 15 years, they gave up and only had about an 80% correct translated. Examples, the spirit is willing, but the flesh is weak, is a saying in the United States. It translated to the wine is agreeable, but the meat is rotten. Out of sight, out of mind, blind and insane, or invisible idiot. And, you kind of know this because you've used Google Translate, all right? And you've put things into Google Translate, and you've gotten stuff back, and you're like, whoa, that is definitely not right. Or you've seen, like, the YouTube videos where somebody starts something in English, changes it to another language, and then changes it back, and it's like, that is definitely not what we started with. So again, it's a really difficult problem because so much of language is contextual, and how do you get a computer to pick up on context? But again, that's where some of those neural networks come in. You evaluate it and you say, all right, either this was a good translation or it was a bad translation, and it tries to figure things out. You kind of saw that if you watched the Watson video that was up there. It had to interpret that language, and from that language, sort of figure out in Jeopardy, what question the answer was actually referring to. But again, a big kind of thing in artificial intelligence. So examples. ELIZA, which is actually what you're going to spend some time with in the lab. One of the first programs to converse in natural language. It used a few tricks to simulate understanding. It would recognize a few keywords, identify categories from some of those words, repeat phrases from earlier in the conversation. And, it's for an early program, it does all right, but it's sooner or later, it just kind of deteriorates into nonsense dialogue. And that's the problem that most of these things have, is that they might be able to keep it up for a little while, but the longer the conversation goes, the easier it is to tell that, like, okay, this person really isn't understanding. Look at that, I just said person. This program is not really understanding what's going on. And it misses the mark sometimes. But you'll get to play around with this a little bit. You'll get to see kind of the premise of how it works, and then you'll get to try to create some of your own rules to try to improve it, if you will. And then again, I just mentioned this a second ago, but we've all seen these stories of like YouTube videos of bad translations. Here's an example of Facebook apologizes after a wrong translation, sees Palestinian man arrested for posting good morning. Again, these will all be links in the presentation that you can click on and look if you want. But we've seen this before, right? This isn't new to any of us. I'm sure if you've taken a foreign language at Ichabod, your teacher has made you well aware of the deficiencies of Google Translate and how you can get yourself into trouble if you try to use it. All right, so natural language comprehension. So just, again, to sort of illustrate why it can be so difficult, single words can have multiple definitions and can even represent multiple parts of speech. This is what we call lexical ambiguity. So the boy hit the girl with the bat. Bat, what are we talking about? Are we talking about the flying animal? Are we talking about the bat? Both of them actually, it's a horrible boy. Like, I don't know what this kid's problem is. Sounds like a jerk. But, like, did the boy, like, swing a bat and hit the girl? Did the boy have, like, a bat and, like, throw it at the girl? Or did the boy just, like, punch a girl that happened to have a bat in her hands? Or did the boy punch a girl that happened to be holding a bat? I'm not sure why she was holding, like, a winged bat, but, there's so many different ways that sentence could be interpreted. So trying to train a computer to, like, understand that is very, very difficult because, again, it comes down to context. A natural language sentence can also have syntactic ambiguity because phrases can be put together in various ways. I saw the Grand Canyon flying to New York. So is that you were flying and you flew over the Grand Canyon, or did the Grand Canyon get on a plane and take a flight to New York? Now, probably not. There's not a lot of flights happening right now, so I don't know why you were on a flight, and I don't know why the Grand Canyon was on a flight. You're both supposed to be self-quarantining at home, but these things happen. And then referential ambiguity can occur with the use of programs. The brick fell on the computer, but it is not broken. All right, what's not broken? Is the brick not broken? Is the computer not broken? There's all sorts of ambiguity in that sentence that we as humans can usually figure out, but a computer program has a far more difficult time doing that sort of thing. All right, so again, just this idea here, why such a problem with natural language? Hundreds of thousands of words with multiple meanings. Natural language programs must deal with rules that are context dependent. These rules for constructing sentences from words are called the syntax. Even more difficult is determining the underlying meanings of words and phrases. And ultimately, what it comes down to is the computer lacks common sense. It's something we take for granted, but our ability to put things in context, our ability to like analyze the situation and respond appropriately, like there's a lot going on there that becomes very difficult to simulate in a computer. So in some ways, we've made a lot of progress, but in other ways, we still have a long, long ways to go on some of these things. So again, you're going to mess around with this in the lab. You're going to interact with a variety of chatbots. You're going to mess around with Eliza a little bit. And you're just going to get a chance to play around with some of these things and just see kind of what's out there. One of the ones that we'll be working with is one that's won the Loebner Prize, which is what we talked about at the very beginning there, kind of the Turing test one. So, that's one of the better ones out there, and you're still going to see that, all right, it does some things well, but in other places it's really kind of falling short. So, for as much progress as we've made in some areas of artificial intelligence, we still have a ways to go in certain capacities. So again, you'll have a chance to play with some of these things. If you haven't watched any of those videos yet, please do. You should be watching the one on Alan Turing. You should be watching the one on 248. The longer ones, I believe there's one on Watson. I'm blanking on the other one. One is from Wired. It's just, I think, on machine learning. I'm blanking on the other one right now. But anyways, watch at least one of those. It'll give you kind of a much better handle on not even just a better handle, but just, a better appreciation of kind of what's going on in artificial intelligence and kind of some of the things that we have achieved and kind of where things are going. Oh, Go, right. The other one was on Go. So there's one on Go, there's one on Watson, and there's one just on general machine learning. So again, pick one of those three if you haven't already, just to give you a little more context for artificial intelligence. Because again, in this class, we did an overview of it here. It gives you kind of a sense for it. But really, it's a field unto itself. And if it's something you decide to pursue in college, you're going to go a heck of a lot deeper than we just went right now. So it's good to just kind of have an appreciation of what's been done, what are some of the techniques, and so on and so forth. All right, so that's that. Good luck, and I'll probably post the lab later this week. All right, bye.